On the horizon are flexible circuits crafted from silk and graphene. Greetings everyone! Today's video focuses on a groundbreaking development by researchers at the Pacific Northwest National Laboratory within the Department of Energy. They have successfully created a consistent two-dimensional layer of silk protein fragments on graphene, which boosts its capabilities for microelectronics. This innovative silk-on-graphene pairing has the potential to produce sensitive transistors suitable for wearable health sensors and memory transistors for neural networks. The research highlights the environmentally friendly water-based characteristics of these materials, setting the stage for biodegradable electronics and enhanced silk-integrated circuits. Now let's dive into our discussion. Following thousands of years of being a precious commodity, silk remains a source of amazement. It now has the potential to lead to an entirely new path for microelectronics and computing. Although silk protein has found applications in specialized electronics, its utilization remains restricted, partly because silk fibers tend to be tangled and resemble a chaotic mass of spaghetti strands. A team of researchers, spearheaded by scientists from the Department of Energy's Pacific Northwest National Laboratory, has successfully unraveled the complexity. In the journal Science Advances, they announced their accomplishment of creating a uniform two-dimensional 2D layer of silk protein fragments known as fibroins on graphene, a carbon-based substance renowned for its outstanding electrical conductivity. Chen-Yang Shi, the lead author of the study, stated, "This research offers a reproducible approach for the self-assembly of silk proteins, which is vital for the design and creation of silk-based electronics." He emphasized, "It is essential to highlight that this system is water-based and non-toxic, making it crucial for biocompatibility." The microelectronics industry has a strong interest in a sensitive, tunable transistor that could be created from a combination of materials known as silk on graphene, particularly for wearable and implantable health sensors. Additionally, the PNNL team envisions these materials serving as a crucial element in memory transistors, or memory stores, which play a role in computing neural networks. Memory stores enable computers to replicate the functioning of the human brain within these neural networks. For hundreds of years, the production of silk from silkworms remained a well-kept secret in China, even as its reputation grew along the renowned Silk Road trade routes, reaching India, the Middle East, and ultimately Europe. By the time the Middle Ages arrived, silk had evolved into a symbol of status and a highly sought-after item in European markets. Even in contemporary times, silk continues to be linked with luxury and prestige. The exceptional qualities that contribute to silk's global fame, such as its elasticity, durability, and strength, have also resulted in its application in cutting-edge materials. Much research has been conducted on using silk to modulate electronic signals. However, the inherent disorder of silk proteins limits the level of control achievable, stated James de Yoreo, a Battelle Fellow at PNNL, who also serves as a professor of materials science and engineering and chemistry at the University of Washington. Given our expertise in managing material growth on surfaces, we wondered, could we create a more effective interface? In order to achieve this, the team meticulously regulated the reaction conditions, introducing individual silk fibers into the water-based system with great precision. By maintaining exacting laboratory conditions, they successfully created a well-organized 2D layer of proteins arranged in parallel B sheets, which are among the most prevalent protein configurations in nature. Subsequent imaging investigations and corresponding theoretical calculations revealed that this thin silk layer maintains a stable structure, exhibiting characteristics similar to those of natural silk. This electronic structure, measuring less than half the thickness of a DNA strand, exemplifies the miniaturization trend prevalent throughout the bioelectronics sector. De Yoreo explained, "This kind of material is conducive to what we refer to as field effects. Essentially, it functions as a transistor switch that activates or deactivates based on a signal. For instance, if you introduce an antibody when a target protein attaches, it results in the transistor changing its state. In fact, the scientists intend to utilize this initial material and method to develop their own synthetic silk, incorporating functional proteins to improve its utility and precision. This research marks the initial phase in the regulated layering of silk on functional electronic components. To support our channel's growth and ensure broader awareness, kindly hit the like, share and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.